Stars dot the night sky, giving an impressive clue to the vastness of the galaxy we live in. I remember being in South Africa on a clear night, far away from any city and its accompanying light pollution. I simply can't describe how spectacular the heavens were. No photo I could show here could possibly give justice to be in that situation, in person, and looking into the seemingly infinite. Some of the dots we see in the sky are stars, all in varying stages of their evolution, and are many light years away from us. But apart from being giant balls of light and energy, how much do we actually know about stars? Where do they come from? Are there different types? And what happens to them eventually? When we think of interstellar space, we often think of a cold vacuum of nothing. And by our earthly standards, it might as well be nothing. But this is not strictly true. Between the stars of our galaxy is what is known as the interstellar medium, or in other words, the matter and radiation that exist between stars. It is comprised mainly of hydrogen, followed by a small amount of helium and trace amounts of heavier elements. It can't be thought of something like an atmosphere. Even in the densest parts, there are only 1 million molecules per cubic centimeter. That may seem like a lot, but in the same space, at sea level on Earth, there are 10 quintillion air molecules. And even in a laboratory vacuum, there are still 10 billion molecules per cubic centimeter. In the more sparse reaches of space, the interstellar medium's density can be less than 1 molecule in a cubic centimeter. But what does this mean in figures that we can wrap our heads around? Well, here's an interesting comparison for you. If you're sitting on a chair, look directly down at the ground. If you were to have a cylinder, the diameter of your eye, drawn from your eye to the ground, there are more molecules in that cylinder than if you were to be sitting at the edge of the solar system and have a cylinder drawn from your eye to the center of the galaxy over 27,000 light years away. Although very sparse, the interstellar medium is thought to make up roughly 15% of the visible mass of the Milky Way. Much of the molecules in the interstellar medium are ionized, and there is a special scientific instrument called WAM that can see the densities of ionized gas in space from our perspective on Earth, and this is what it looks like. This gives you a perspective that there is a lot more matter in the galaxy than you might initially think. The interstellar medium, particularly dust, has a very real effect on us too. Over vast distances, the dust in the interstellar medium acts like a fog, either blocking the view of stars thousands of light years away in the visible spectrum of light, or giving stars a reddish appearance. If there wasn't an interstellar medium between the stars, you would be able to see the entire disk of the Milky Way in the night sky. As I mentioned earlier, the density of the interstellar medium varies greatly around the Milky Way. If you've been watching my other videos, you may have heard me speak about nebulae and H2 regions. Nebulae are denser regions of the interstellar medium. Some of these regions appear as holes in the night sky. In actuality, they are massive interstellar clouds of gas and dust. And when I say massive, I'm talking many light years across, some many million times the mass of our Sun. You may have seen this famous Hubble image before, called the Pillars of Creation. What you're looking at is an example of these gas and dust clouds. What you can see of the left pillar in this image is 4 light years long. Just to give you some perspective, 1 pixel might just about cover the distance of Neptune's orbit if our solar system was placed right next to the pillar. Incredibly, however, this image is in fact just a small segment of this H2 region called the Eagle Nebula. The nebula is just one of many stellar nurseries where stars are formed in our galaxy. In the background, you can see lighter colors of greens, blues, and reds. These bright colors represent different ionized molecules and are known as the H2 region of a nebula. In this image, greens are hydrogen, red are for sulfur, and blue for oxygen. The electrons freed by the ionization process are continually absorbed and re-emitted, producing the different colors for the different atoms. This is a very similar process to what happens in a neon light. The particles are excited to a higher energy state and eventually release that energy in a wave of light. These molecules are extremely hot, heated by nearby stars to temperatures over 8,000 degrees Celsius. They are also reasonably dense for the interstellar medium, from 100 up to 10,000 molecules per cubic centimeter. The pillars themselves are known as molecular clouds, the densest regions of interstellar medium, from around 100 to about 1 million molecules per cubic centimeter. These clouds are cold and dark at around -260 degrees Celsius, and they don't allow light to travel through very easily. In fact, they would be invisible if it wasn't for the fact that some are silhouetted against brighter H2 regions. Because of the density of the molecular cloud, the inner molecules don't interact so much with the UV light of local stars, meaning the molecules stay cool and dark. Incredibly, it is these clouds of molecules and dust that eventually turn into the same type of stars that dot our galaxy universe. But how? What exactly is the process? Generally speaking, these clouds are stable and would exist for billions of years doing nothing. Look at this example of how gas behaves in a molecular cloud at -260 degrees Celsius. Even at this temperature, with very little gravity, the molecules spread out in the cloud, the shape of the cloud supported by a balance of its own gravity and internal pressure. So in order for these clouds to become stars, there has to be a trigger. And there are a few different types of triggers that are thought to kickstart the star-making process. Going back to the pillars, you can see one of these triggers in action in this very photo. Along the outside of the pillars, you can see a sort of aurora of light around them. This is because UV light from hot and bright local stars are blasting the outermost molecules, exciting them to higher energies, has a weathering effect on these otherwise stable clouds, as the excited molecules either escape away from the clouds joining the H2 region, or they push against the colder molecules further in, compressing them. This pressure can also be created by a supernova shockwave. A supernova is caused by the death of a massive star, a topic we'll come to later on. It's interesting to me, though, that the death of a star can trigger the birth of others. You may also remember me talking about density waves in previous videos, and it's thought that molecular clouds passing through the Milky Way's density waves can also be the trigger for these clouds to collapse. On a very grand scale, galaxies colliding can cause what is known as starburst within the galaxies. Starburst is when a galaxy produces stars at an extremely fast rate, and it can be seen in these areas of extremely hot blue stars. All these triggers destroy the equilibrium of the cloud, and the internal pressure starts to give in to the gravity of the cloud. This bumping and shoving of molecules within the dense cloud cause the molecules to clump together under their own gravity, gradually growing bigger and bigger as the gravity increases and more molecules are pulled in. Depending on the size of the cloud, there can be hundreds to millions of these clumps that get formed within the cloud. As the density of molecules increases from the initial trigger, interaction between the molecules also increases. The temperature starts to increase. The higher density causes stronger gravity. More molecules from the cloud get pulled in by the increasing gravity. Temperatures rise and gravity continues to increase. The domino effect continues. These clumps in the molecular cloud are the beginning of stars called protostars. The protostars keep getting bigger as long as the molecular cloud surrounding them keeps feeding the material. And to become a true star, a protostar needs to be at least 0.08 solar masses. Should the molecular cloud disperse too quickly, the protostar will become a failed star, or what is known as a brown dwarf. The difference between a failed star and a main sequence star is if the temperature and pressure in the core of the star are hot enough for nuclear reactions to begin. Protostars create energy too, but their energy comes from the impact of material entering the star. A star will hit the main sequence, or the next stage of its life, if the core begins to fuse hydrogen to helium. A brown dwarf doesn't have the mass to do this. As a result, it isn't as hot as a star and will keep cool enough. They are not very bright in the visible light spectrum, and would actually appear magenta, red, or orange. They can have planets, but the chance of life on those planets is slim, as the habitability zone would be quite small, and would move closer and closer to the star as it cooled. But what happens if there is enough mass to form a main sequence star? As material gets sucked into the protostar, the star begins to rotate, and material begins to spiral inwards. There are a few objects NASA have photographed that are thought to be protostars where this can be seen. These two arms going into the protostar, impacting at tremendous temperatures. This in turn causes the protostar to rotate faster. The material surrounding the protostar flattens and turns into what is known as a planetary disk. Clumps start to form in the disk too, building up under the same gravity that caused the star. Smaller clumps may build up to become the star's planets. Bigger clumps may begin to form their own planetary disk and may become another star. In fact, this is the most common thing to happen in star formation, our Sun being quite unusual in that respect. Most stars will be in a binary star system. Some stars will have many stars in the same system, all orbiting each other. Had Jupiter been fed more mass during its birth, it too might have become a star. It would have needed a lot more mass though, about 70 times more than it currently has. We should consider for a moment size scales. A typical interstellar cloud is 100 trillion kilometers across, or roughly 10,000 times larger than the size of the Sun system. A cloud fragment which forms one or a few protostars is 1 trillion kilometers, or roughly 100 times larger than the size of the solar system. By the time the core of the fragment has become a protostar, its size will be approximately 10 billion kilometers and its temperature of order 10,000 degrees Celsius. Interestingly, as material is fed into these protostars, they can emit shock waves into the rest of the molecular cloud they're still surrounding. This in turn can trigger further gravitational collapse and more protostars can be formed. Eventually, the molecular cloud's material will be exhausted, and depending on the size of the cloud, what is left is a star, several stars, a few hundred stars, thousands of stars, or a whole supercluster of millions of stars. Some of these clusters will eventually disperse, and the stars will simply join the rotation of the galaxy, much like our Sun. Although I've talked about all of this matter-of-factly, this is still only a theory of how stars are formed, as actually seeing the formation of a star is very difficult due to the timescales involved, and the fact that these protostars are surrounded by dust that obscures the view. This is one of the huge advantages of the James Webb Space Telescope, due to be launched in 2019. Its ability to see in the infrared gives it a big advantage over Hubble, in that it will be able to see through the thickest of dust clouds and hopefully see protostars in action.